Okay, morning. And just as a quick summary of where we were, in the end of last class, on Monday we did derive why the conductance or for a 1D conductor in the ballistic limit the conductance, or we've calculated the current to be, there were spins and valley degeneracies, but just to simplify it with one valley and spin of 2, we found the current to look like this, right? To 2q squared by h, which is effectively a quantum of conductance times the voltage, and therefore and the picture we had at that point that I was using is you have a left electrode with a left chemical potential or a Fermi level, and a right electrode with filled states all the way till the right chemical potential. The difference is the applied voltage, right? And we essentially, in this process of calculating the current, we did make use of quite a few concepts, such as what do we mean by application of voltage, the fact that current only flows within this window of left and right, and then at finite temperatures a little bit away from it, but this is the most important window. And if there are no states inside in the channel within this energy window, then there is really not much current flow. Later on, perhaps next week, we're going to start looking at if the two metals are close enough, then you can actually tunnel directly rather than needing states in between. And that's also the second problem in the current assignment you have, right? I mean, it's effectively the same problem as the earlier one, except you are supposed to calculate the current now, not just the transmission probability. Right? Now, there were a couple of questions, I think, in the end of the class that, look, if I actually have the conduction band edge that kind of smoothly and continuously goes like that from the left contact to the right contact, right? So let's say I have a semiconductor and here's the gap, and in the metal all these states are filled, and then all the valence band states are filled in the semiconductor, and then also these are here. So the question is how, I think there was a question at the end of the class, after the class, that how does, we said that I can have any distribution of the semiconductor I want, but I was drawing a picture that looked, something like that, right? E versus K, and the arguments we used was the right going states are filled by the left electrode, the left going states are filled by the right electrode, and then you kind of sum and get the current. But there was one question that, look, if you have ballistic transport, this part it's a gap, right? If you look at this is a gap. So how can I even fill this state here, right? You can see that in order to fill that right going state in the semiconductor, the metal electron, if the electron comes in from here, then it's going ballistically. It has no way to relax to that state, right? It cannot lose energy, right? Because energy, everything in the y-axis is energy here, right? So on the other hand, this state, if I do not allow energy relaxation in the channel, this state can only be filled by a state which is here. Do you see that? Right? I mean, at the same energy. It can only be filled by that state. And this is something we're going to look at in quite some detail later on. But I think you will realize that if you sit for long enough, meaning if you give it DC behavior, what's going on here is you have electron waves that are incident on this barrier, and then they get reflected, incident, reflected, and there's always some probability that you can tunnel through. There's always some probability. So in other words, an electron state in the metal at this energy, it's not a bound state, meaning it's not really bound. It's called a quasi-bound state. Given enough time, it will leak out, and it will go there, right? Because that's the real end of the problem, that you will leak out. The question is, how long will it take? And we'll see later on, if that time it takes is very long, that's the heart of memory devices, like the flash memory that enables all the handheld, laptop, iPhones and iPads today If it takes very long, then you use it as a memory. If it takes relatively short time, you use it as a good contact, and things like that. So good ohmic contact, and so you can turn it back and forth. And the other picture is in order to calculate the current, the arguments I was using, the best point in space to use that argument is right at the what's called this injection point, where your semiconductor starts. And you can see that these questions can get a little hazy if you go down to atomic lattice constants and all that. But if you just consider that the semiconductor right here, right at this injection point where the semiconductor band starts bending, at that point there is not much confusion, right? There is not much confusion because there indeed all the right going states are filled by the metal. There's no barrier. All the left going states are filled by the tail, right, of the right contact. There's not much confusion at the source injection point. So that would be called the source injection point, and we'll see this point plays a major role in understanding the ballistic transistor, whether we make it 3-terminal, and we're going to look at that today. Okay, so which is called the source injection point. Now, downstream here, you can still see, and then this is actually a nice exercise, and I must say that I have not seen that at least done in a way in either papers or books. You can still, remember, the one thing about current is it is continuous. Whatever is the current flowing here is the same as current flowing here, is the same as current flowing here. Right? So down here, if you, for example, are in a situation where tunneling has not kicked in, then you can see that you do fill a little bit of some states out here, which is whatever is the tail of the left electrode. You fill those states. On the other hand, you fill a whole lot more of the left going states because they're so much closer to the Fermi level. The tail is stronger here, right? But then there's a difference because these states, which are carrying current to the right, are moving much faster, right? You have less carriers, but they're moving much faster. You have more carriers, but they're moving slower to the left. So, such that the difference will always be the current here. And then this is something you can calculate, and then find out what is the separation of the quasi-Fermi levels, and what is the electron distribution here, and all these things you can find out by just maintaining current continuity across this. So, is that clear? There will be, if there are some questions or doubts, that's actually good, and you should feel free to please ask. And we will be looking at some aspects of it throughout the course, sooner or later. And then this is for single particle picture, and then you bring in correlated effects and similar things. We'll be asking a lot of questions about these things later on. Any questions on this? I know any further questions? Well, okay. If not, let me just say that this result that we came up with, that the kind of the quantum of conductance, you can turn it upside down. The experiment, by the way, which was done in 1988, right, which showed that indeed you get 2q squared by h or 2e squared by h conductance, but in steps. And I want to discuss a little bit about those steps, and then take those steps forward to from 1D to 2D, and realize that a ballistic transistor is essentially the same thing here, but essentially you have added a third terminal to it, a gate, and you have made it as if there are a lot of 1D channels, but not exactly like that. It's because indeed you have a 2D channel where you can, and I'll explain the differences, but this is kind of the heart. So every time you allow, for example, this may be in pictures just one 1D conductor, and then you can think of if I had two 2D conductors, or 3 or 4 or m, right? If I have m modes, right, then my conductance will be m times this. Right? So, yeah.
Just a quick question. When you draw the linear band diagrams right there, those are a function of x, right? And the other ones are a function of k.
That's correct. This is it's real space, and this part, which I'm plotting, is E versus k. And if you remember, we wrote the effective mass equation, that energy is EC of R plus E of k, meaning the potential energy plus kinetic energy. So that's the separation between the two. That's right. Yeah. So in that picture, the electron, as it moves along, is losing potential energy, but is gaining kinetic energy. Its energy is the same, right? So it's yeah. So in that picture, you can imagine the wavelength. It started out what was very long, and then as you go across, the wavelength really gets very, very short because its kinetic energy is going up, right? So it gets really compressed, the wavelength-wise, yeah. Okay, so if you have m of such conductors in parallel, then we know that the conductance, total conductance, will be m times the conductance of 1, something like that, right? That is clear if I had really made them in parallel, right? But even within one conductor, if I've made it with a semiconductor, I think you remember that if I take a semiconductor and I make a quantum wire, then my energies as a function of k for 1D. So a physical quantum wire, I would be making that with either a carbon nanotube, or I would take a heterostructure and etch and try to make it. So essentially, a physical 1D conductor would always have some dimension perpendicular to the conductor. Right? So there will be some dimension which is perpendicular to the conductor. Does that make sense? I mean, physically there will be some dimension. And because of that, there is no, within a single conductor itself, you can have multiple modes. Multiple modes. What does that mean? If you remember, we wrote, if I have, let's say, a length along this direction, so let's say that's x, and this is Ly, and that is, the vertical dimension is Lz, right? So maybe you can tell me, how do I write my EK diagram for this situation? Here's my x direction, and y and z, they are, quantized. They are very small. So how do I write my energy dispersion, EK diagram? Maybe you can help me write that now. So, see, the first thing is I want to identify which direction is free, right? And here, the x direction is free, right? So the total energy for that would be, what would be the component of energy along the free direction? So, right? How do I write that?
Kx squared.
Right. So the kinetic energy along that direction is just, let me write it this way, h square kx square by twice. And I'm now making a lot of calls on stuff we have learned, which is we have to use the effective mass, not the free electron mass, because it's in a crystal, etc. Right? Now, if I have started with a semiconductor, let's say this is gallium arsenide, and surrounding it in all other dimensions is aluminum arsenide, which is a larger band gap semiconductor, and this is a smaller band gap semiconductor, and we're looking at the conduction band edge. And as I go in here, there's a drop, so it's like a potential well. Let's make the assumption it's an infinite well. It's an infinite two-dimensional well. So I will start with the conduction band edge of the gallium arsenide plus a certain ground state quantum energy, right? So the ground state quantum energy, and that ground state quantum energy is going to give you, various modes. That's what's going to give you various modes. These are the various subbands of the. Let me write it this way. So you will have k y squared plus kz squared, but remember ky, if I look at the y direction, you can fit this wavelength, that's one mode, that's another mode, Do you see there are multiple modes now that you can fit along the x, and along the y and along the z. Therefore, what you end up getting here is ny squared plus nz squared, where n's are integers, and then you get some other factor which is, pi over lx and lz's and all that, right? And so for each of these integers, the minimum integer allowed is, as you can kind of imagine, if this is the minimum one that you allow, then there is a ground state. It's not 0. N is not 0. Right? Does that make sense? So as a result, for each pair of such integers, you have one mode. And if you fill up the energies, if I plot the E versus K instead of just one, I actually have another one of these. Each one of them goes like this, but then the minimum is different, right? So that's another subband, and so on. So in a real quantum wire, you have these situations. And now you can see that each of these subbands is going to give you 2q squared by h, right? And then if you have m of them filled, so if your chemical potential was, of the left side was here, so depending upon how you fill them, you can have if your Fermi level was here, then it would be 1 q square by h. If it was, the left Fermi levels were here, the right Fermi levels were here, then you can see, so you can have 2, and then you have transition, you have abrupt transitions as you go across. Do you see that? And then that's exactly what's happening here, where they are going through 1 mode, 2 modes, 3 modes, and so on. So, and then they're changing that. How are they changing the occupation of these modes? Well, by changing the gate voltage, now the third terminal, which is what fills this up to a certain level. If you have one. So that's really the picture. And what I want to do is very briefly today make a connection to something we started out, I think, in the first or the second class. That this is obviously looks very different from the Drude result or Ohm's law, right? Because Ohm's law is V is equal to IR, and that's something. And if you remember, we had asked that experimentally, if I take a conductor and I start making its length L, if I make a conductor and then making its length smaller and smaller, then what is, for example, let's say, what is the resistance, right? What is the resistance that you see in a conductor as you make it, smaller and smaller? And from here, you can see that I have no scattering anywhere, and I still have what looks like a resistance. I is, it's not a, there's still a resistance, because V over I is still H over 2Q squared. Right? So it's not 0. I mean, resistance is not 0. Or in other words, from taking this here, I can write that the resistance of a ballistic conductor, if I have M modes, is H over 2Q squared times 1 over M. Right? If I have multiple modes, then I will have lower resistance. Does that make sense? I mean, it's just 1 over that. And now, on the other hand, if you remember, Ohm's law says that if I take resistance, so that's your ballistic, kind of quantum result. And Ohm's law says that it should be rho L over A, right, where rho is the resistivity, right? And then the question is, how are they connected? Because I think we know that anything in the microscopic quantum picture should go over to the classical picture. There's this correspondence principle. So there must be some connection between the Ohm's law and these multiple modes. So in other words, Ohm's law is saying that, well, if I do the experiment, I am expecting to see this, and but when you actually do the experiment, what you see is for large lengths it does look like that, but at some point it saturates, and you cannot go below a certain limit, and that is, that's your, this cannot go below that, right? So, so the resolution to this, we'll just discuss this now, and that will really motivate some things we will do in maybe 2 or 3 weeks from now, which is the whole, machinery of Boltzmann transport, etc. We're going to look at that, which involves scattering. But the first short picture is very straightforward. What it's saying is the way we are going to reason it is the following. So we're going to go from, instead of coming from here to here, we're going to go bottom up. We're going to look at the quantum result and then kind of see, can I explain the classical result by going to many, many modes and invoking some arguments. Right? So just as a point of argument, H over Q square is actually not, I mean, when we think quantum is supposed to be very small, very, very small, but it's really not small. H over Q square is about, 25 kilo ohms. It's not small at all, 25 kilo ohms, I mean, right? Obviously, if you have a lot of modes, you can make it way smaller, right? So it's not, okay. Conductance reaches a maximum and resistance reaches a minimum. Right? Does that make sense? Sorry, resistance, what am I saying? Okay, forget about what I said. There's no maximum, minimum. I mean, but you can change the whole thing by modes, right? By just changing the number of modes, yeah. So, but the one thing is, any resistance you measure is kind of not going to go below that. That is actually true. Meaning if you have a single mode, you cannot go below that. That much is true. Right? So, okay. So the picture then one can use here is that I do have multiple number of modes. Let me just write this down. And by the way, this part is I think it's covered, and I will in the first few chapters of the lessons in nanoelectronics from Supriya, the book I have prescribed, very nicely. So please read that. It's done nicely there. So the resolution to this is really, and this is something we're going to end up with later on when we do the Boltzmann transport. We are going to see that if I allow scattering in the channel, meaning if I don't allow, assume that it's a ballistic transport, but I do allow some scattering in the channel as the electron moves along, meaning it goes a certain length, and then there's some amount of scattering. Maybe it gets deflected backwards or at an angle if it's going in 2D at an angle, and then so every length, say lambda mean free path. A certain mean free path it can move, and then it'll scatter either because of phonons or because of defects or something of some perturbation to the perfect periodic crystal. If such things happen and the length of the channel is L, then we will see that the end result, this quantum result, will get modified slightly, and it will look like this: h over 2q squared, still 1 over m. But there will be an additional factor here, and that is just 1 plus the length over the mean free path. We're going to see that later. That's the only modification that's going to happen. And this essentially kind of handles both situations, because if you have a very long conductor with a lot of scattering, then you can forget the 1. All right, so you can forget the 1. And let me write those two limits down, and that will tell us something very useful of what do we mean by modes, because we're going to use that idea to connect to the Ohm's law here. Okay, so for a ballistic limit, there's really not much to discuss. For the ballistic limit, when the mean free path is very, very long, right? So this term is very small, and you have what we just derived, right? And that's not a problem in the ballistic limit, so we get it already, right? So whereas in the long length limit, in the diffusive limit, that's the Ohm's law term. So diffusive limit, when you have a lot of scattering or a random walk sort of motion, there the mean free path is very short. So this 1 is neglected, and your resistance therefore becomes equal to, or close to, h over 2q squared, 1 over m times L over lambda mean free path. Right? So that's how it will look like. So the question now is, what is this m? Right? What is this m? And because we are doing this, let me also write it here, because it will tell us something very useful right away, something that we measure routinely in experiments today. So what is this m? And we have seen that if I look at a 1D conductor, this m is kind of the number of modes, how many modes you fill, right? And you can generalize it. You see, this is really, if I really look at it as area, cross-sectional area as length, then these are really not for a 1D conductor. Right? This is for a 3-dimensional conductor, right? So this is a 3D conductor where we have a cross-sectional area and the length is L. So how do we think about the number of modes in a 3D conductor or for any general conductor? So it's again, what is the number of modes? Is the number of waves that you can fit, right, inside the physical dimension. Right? It's the number of waves you can fit. How do you control the number of waves? That you control by what is the density of electrons. If your electron density is very high, you can see that you're going up in k. Right? Your k is going up, so the wavelength is getting shorter. Right? So for any given physical dimension, you can fit more. Right? Does that make sense? It's just an intuitive way of thinking about it, that if your number of electrons is high, you will always be able to fit more modes in the same window. So the m will increase. Right? So the m should increase with the number of electrons, but at the same time, the physical dimensions of it really play a big role. So what I'm going to do now is look at it in 2D, and then you can see why we'll make the connection to 3D as well. Right? So, and then in a way, we have started talking about the ballistic FET now, because there it's the electron gas. So instead of 1D conductors now, let's look at 2D and look at what do I mean by the number of modes. So in 2-dimensional space, I'm going to just draw the k-space picture. K let's say along x and k along y, and this direction is x for us. Right? So we've written this is x. Now we're looking at a cross section, and now I have a 2D electron system here in the semiconductor. I have source contact, drain contact. I have electrons going in, and I'm asking now if the first question I will ask is, let's for a moment forget I've applied a voltage. My voltage is 0, but I have put electrons in here. And how much electrons have I put? I have put an electron with a density n sub s, which typically in semiconductors, when we turn on a transistor, it's of the order of 10 to the power 13 per centimeter square. That's the sheet density of electron, two-dimensional electron gas density that we create using a gate, or sometimes using some other techniques, polarization, modulation, doping, something like that. We create this electron gas. Okay? So in the process of creating this electron gas, how have I filled the K space, right? I mean, remember in K space, if I have a 2D electron gas in a plane, so the picture really should be, I have a source contact here, a drain contact here, and then I have, this is my 2D electron gas. Let's say that length, is L, and the width is W. So the length is L and the width is W, right? And so if that's the situation, what can I say about Kx and Ky? They are, basically discrete, right? They're like 2 pi by L and 2 pi by W. They're quantized according to that. So essentially, again, I have a set of modes that allowed K values that look something like that, right? So yeah. Anyway, so the spacing between the various modes, origin and all these modes, right? So the spacing in the y direction. Let's just draw a couple more. The spacing in this direction is 2 pi by W, right? Where that's the width of the 2D system, and in the x direction is just 2 pi by L, right? And now this picture is when we say I'm filling in some electrons into these modes, you can see that if you have taken any course in electromagnetic theory, or I think we had a little short course in summer, and we kind of discussed this as well, but we're going to do a little more detail in this class. Each of them is an allowed mode for you, right? So each of them has a different wavelength, right? And each of them is allowed mode, which ensures that the wavelength of the electron exactly fits this dimension, right? So each of them, one of them like that, and as you go to higher and higher Ks, it gets more waves in the sense. It just fits, right? And it's exactly the same problem as an electromagnetic waveguide, or if you have done any course on, optical fiber or microwave waveguides. It's exactly the same problem. So how many modes can you fit? That is completely determined by the dimensions, right? WL. And or rather, the allowed modes are completely determined by the dimensions. And since now you see very interestingly, first, why are electrons behaving like light? Because that's the heart of quantum mechanics. They have wave-like properties. The second is now you have to fill these, and you have to end up with this many electrons per centimeter square. Now, if electrons were not fermions, you can put all of them in the first state, right, and game over, right? But they're not. They are fermions, right? They obey Pauli exclusion principle, which is why you can only put 2 here, right? Two in pure numbers now, 2, and then, but you have a lot more, so you have to keep going now, right? Keep going, and you fill up to a certain amount of, case. In the K space, this shape, is basically you have a Fermi circle, and at 0 Kelvin at least, all the states inside the circle are occupied, and all the states outside are empty. So just so that I connect back to where we were, I'm trying to actually calculate the modes, and I'll show you right now. It's very easy. Once you physically realize the geometrical connection, the number of modes is trivial after that, right? So you see, you fill it with this much, and all you have to ensure is, if I have each state holds. Actually, if I ask the question, how many electrons are there in the kth state, right? K here is kx, ky. What's the answer to that? It's the Fermi function. is the Fermi function, right? Fermi Dirac distribution. So f of k is the number of electrons in that mode, right? And how many total electrons are there in the whole inside this, kind of the Fermi circle? And I hope you understand. At 0 Kelvin, it's a perfect circle. At high temperatures, it gets smeared out with a KT tail and all that outside, right? But if you want to now, if I ask you what is the total number of electrons, then you have to sum over all k states, right? Sum over all k states, all the points. If I have 2 here plus 2 plus 2, I mean all of them, I just add up all of them. That's the total number of electrons. But I'm not interested in number. I want the density per centimeter square because I'm looking at something big, and I look at the so the density obviously will be the sum divided by the area, right? W times L. That's the density, and that should be exactly 10 to the 13 per centimeter square. That's and what that uniquely determines is obviously, as you can see, what is this Kf, because that's the unknown here, or what is the Fermi level or the chemical potential of this. It completely determines it. And there will be some other parameters, like spin, and if you have valleys, you just make sure that you kind of sum it properly. And this sum, let me just evaluate it right there, and we come back. So f of k, let's look at, for argument's sake, at the 0k limit. At the 0k limit, now, by the way, this is exactly doable. If you remember, I claimed last class that this is a zeroth order Fermi Dirac integral. You can do it exactly, right? Yeah, so this you can do exactly. But I'm just going to look at 0 Kelvin because that simplifies the problem a great deal. So when I sum, remember, I'm going to again convert it into an integral. I get a spin degeneracy, and there's maybe a value degeneracy. Convert into integral, but now I'm integrating over kx and ky. Right? And what am I integrating? I'm actually just integrating the function 1, because Fermi function is 1 all the way till the Fermi kf, and then it's 0 after that. Right? So I want to find kf. That's what I want to find. Right? And remember, our normalization factors are 2 pi by L and 2 pi by W whenever I do an integral like that. Right? Whenever I do that integral, and you can see these go away, right? And what you end up getting is, and remember, we are going from 0 to infinity in principle, but at 0 Kelvin, you cut it off abruptly. The kf, below kf, f is 1, and above kf, it's 0. So you just cut it off, right? And you get gs, gv over 2 pi whole squared times kf squared by 2, right? Is that correct? So you get, it's the area of the circle, right? This, whatever is inside the integral, is the area of the circle. And the area of the circle is pi k f squared. Makes sense, right? And what I'm doing here is actually perfectly general, meaning if you have graphene, if you have any 2D system, as long as you know how many valleys there are and spin, there is no argument of energy here. Very important, no argument of energy. This is just mode fitting. There's no energy argument, meaning the band structure is not playing a role yet at all when you look at the carrier density. And from here, you get that kf is, you can maybe 4 pi. Okay, so if I take a spin and a valley degeneracies which are normal, valley degeneracy of 1, spin of 2, what you'll find is kf goes as 2 pi square root of carrier density. That's the maximum. So it's a very simple relationship. Kf is square root of 2 pi times carrier density. So if you know carrier density, you immediately know what is the kf. You also know right away what is the wavelength of the electrons with the highest energy here, because that's 2 pi by wavelength, right? 2 pi by wavelength is kf. And you can do the calculation, and you'll see that's like about 20 nanometer or so. That's the wavelength of those electrons, right? So at the Fermi wavelength. So anything below 20 nanometer, you start really discretizing it again, and you have finite modes and so on. And you can now say how many modes there are. How many modes are going here? Now we can see that it'll be very interesting. Is this clear, by the way? I mean, I'm pretty sure I've seen this in many. Now, if you go to 3 dimensions or in 1 dimension, you can see the results will change, right? One way to just remember how it looks is in 2 dimensions, carrier density goes as per centimeter square. You can just do a very simple dimensional argument that a kf is always 1 over length, right? How do you get 1 over length from 1 over length square, you take a square root. Right? And there's a pi, and all these are geometrical factors after that. In 3 dimensions, you have a sphere instead of a circle, like a Fermi sphere, right? And there you have 1 over centimeter cube, and how do you go to length? Well, you take cube root, right, 1/3. So there'll be kf to the power 1/3, and there'll be some other pi factors outside. And in 1 dimension, carrier density is 1 over length. That's directly related to kf. N and kf are linear in 1D. Right? So that's, and this is whatever I'm saying here is absolutely independent of whether you have graphene, topological insert. It doesn't matter. This is just a case-based picture. We haven't even talked about energy dispersion. Right? So it's completely general. Right? Okay, so what's the number of modes? This is kind of the thing you can do right away now, because the number of modes has a very physical meaning now. See, let's look at just this slice, because we are going from source to drain. Electrons are going that way, right? From source to drain. So you can now think of this picture as many. Here's a 1D channel. There is a 1D channel. We have already calculated the 1D channel conductance is 2q squared by h for one mode. Does that make sense? For one mode. And when I'm saying that, if I look at just this mode and forget about everything else, that's a 1D mode. Right? And you can now kind of start seeing that if I look at this layer, all these slices are effectively like 1D modes. Right? They look like 1D modes. And now, what is this M? The M is how many modes there are. That is it. How many such lines do you have, right, geometrically? And you can tell me what it is, because you see, how many lines do I have? It's this length divided by this length. Right? That's the number of modes. Right? So from here, you can see that the M, how do I write that here? Okay, so from here, the M, let me erase this part. For the 2D case, the M becomes, what is this length? It's 2 times kf, right? 2 times the Fermi wave vector, divided by 2 pi by w, right? So that's the number of modes for this. As you can see, it may not be an exact integer, right? So, right, because it may be that is, but you can, by the time you reach this sort of numbers, you are talking about, maybe we are talking about numbers where a factor of 1 doesn't matter really. I mean, so it's a very large number typically. So essentially, this becomes kf times w by pi, and that's the number of modes for you. And does that make sense? I mean, that for the 2D system, that's the number of modes for 2D. And you can kind of project for 3D. It will have some other power law dependence on kf, and and it will have, instead of the width, it will have area, cross-sectional area, right? Do you make sense? I mean, and that will relate to rho L by A, all those things. So so essentially the modes. So what we just found was, for 2 dimensions, the modes goes as the width, right? Does that make sense? The number of modes goes as the width of the channel. Right? For 3D, it will go as the area, right? And that's where that A will come from. Right? So that area and so on. So now kf times width over pi is also, you can write it in terms of the carrier density. So essentially, it goes as square root of the carrier density times the W, and there's some other factor outside in the front, right? So that's M for 2D. And you can go back here, look at the quantum conductance, and say that what is my 2D, two-dimensional quantized resistance, or so you say h over 2q square times 1 over m, where m is just that width, square root of carrier density, and all these factors of pi's. So some factors times, did I do this right? M, yeah, times w times square root of ns, right? Or the carrier density. And you can actually take the width to make it completely physical and take it here, w times the resistance of a 2D conductor. And you see that the stuff here has units of ohm times micron, or it's called the contact resistance. It's basically this contact resistance. Ohm, micron, or milliohm, millimeter. I mean, depend on how it's resistance times length. It has units of resistance times length. And on the right side, you have basically Planck's constant, electron charge, and carrier density, and some mathematical factors of pi's and all that, and nothing else, right? So that's a very fundamental result, that the contact resistance of a 2D system, for example, will go as 1 over square root of the carrier density that you put in it. So if you put more electrons, the resistance is lower, and what is very important is this resistance is, for the given carrier density, it is the minimum you can have. You can't go any lower. Does that make sense? I mean, this is the ballistic resistance, right? So you cannot go any lower than that. And this, used to be obviously just an academic exercise earlier, but nowadays it is a big problem, in some sense, because if you look at, so just as an example, just as a summary, this is results from our research group working on gallium nitride, where we have a 2D electron gas. We essentially keep increasing the carrier density. And here's the, what I just derived. Resistance is, all this h and square root of carrier density in the denominator and some other constants, right? H over q squared, and then square root of carrier density. And when you do the numbers, you get, if you remember, with the 26 kilo ohms is the, h over q squared. And so you get 0.026 ohm millimeter. So that's kind of the result you will get, times 1 over carrier density. It's all non-dimensionalized here in some sense. So if you have 10 to the power 13 per centimeter square carriers in the 2D system, then your contact resistance is this much. And this used to be a very small resistance, maybe about 8-10 years ago. But now the channel is so small that there's no resistance in a transistor. I mean, it's already like 10 nanometers now. So there is no resistance in the channel. All the resistance is this. And you have hit some sort of a limit, because you can't go below this if you have a perfect crystalline ordered material. At least that's what the theory seems to be saying, that this is your minimum of resistance. And this is dominating the resistive loss now in the device, because this channel is already so small, right? So it's a very important thing. And anyway, by the way, so this is also very general. You can look at graphene, gallium nitride, silicon, InGaAs, all kinds of semiconductors. If you look at this problem, this is the dashed line is very simple plot of what we have here. This is a straightforward plot. You just make the plot here, through technological development, most of the materials have kind of managed to get down to this limit. But what I'm trying to say is even that is posing a barrier now, meaning that's become a source of problems. Meaning you have to, if there are ways to go even below, that would be nice, right? So that's what I mean to say. And just to be sure, this is the quantum limit for crystalline material. Right? So there's maybe a hint there that if you make it somewhat partially non-crystalline in some regions, you can maybe break this limit. We don't know yet. We don't know. So any material system, for example, today a lot of people are working on these transition metal dichalcogenized like moly sulfide and selenides. The resistances, at least till 2 years ago or 1.5 years ago, were very, very high, 2 orders higher. Now they're about 1 order higher, but there's still a long way to go. Meaning, till you actually reduce the resistance, when you make a device, you are mostly measuring the contact resistances. You're not really measuring the internal part of the device yet. So you're not seeing what the material is capable of. You're making, just like when you start saying, "Oh, I have been to Amsterdam," but you've only been to the airport. So that's the same thing, right? So you never see what's going on inside because you're still limited by the contacts right now. So yeah. So anyway, okay. So this is kind of an important point, and I hope you can now see that if you had various other dimensions, how it will scale. I mean, it will give you this diffusive result because m, the number of modes, depends on the cross section through which you are going through, right? So if you are in 2D, your cross section is the width. If you're in 3D, it's the area. More is the area, more is the number of modes you can fit, right? So that's where and this rho L by A, that essentially this form will become that, is what I'm trying to say. So there's one more aspect of it which we'll talk about later, which is compared to ballistic transport, diffusive transport looks a little different, right? So okay, so what I want to now say, and we are kind of started talking about the ballistic FET now, is I kind of cheated a little bit by saying that what I said is absolutely correct, that the number of modes is just exactly that. But this situation that we have here, where I have a number of modes that are, is really not the same as if I had m 1D conductors. It's not the same. Physically, what's different? If I have m 1D conductors separated from each other, none of them are going laterally. They have no chance of electron from here to go from here to there. That's not allowed, right? Whereas here, if I look at an electron occupying this mode here, the velocity of that electron, if your energy, if you have a parabolic band, say, the E versus K is h square over 2 times effective mass, isotropic, and kx square plus ky squared, then the velocity, groove velocity of any k state is 1 over h bar times the gradient, right, of this in the k space. And I think you're doing this in your first assignment as well, is 1 over h bar times d, this over dk, but really it's a gradient, so the way you're doing that is taking, say kx unit vector d over dkx. I'm just writing it out in its full glory here. Ky d over dky, right? So that's Cartesian coordinates kx squared plus ky squared, right? And once you are done with that, what you get is h bar over m star, right, times kx times the unit vector along x plus ky times unit vector along y, right? So that's your group velocity of any k state. And this is a very important parameter which we are going to now use to differentiate between a real parallel connection of many 1D conductors and then calculate the current of a ballistic transistor now from here, right? Okay, so here you see the moment I ask the question, what is the velocity of that state of the electron that occupies this mode, immediately the one question that had not mattered till now, what is the band structure, comes into play. What's the band structure, right? So if you have graphene, it will be something. If you have parabolic band structure, it will be something else, right? And right now we have this. For other materials, it will be something different, is what I'm saying. So the group velocity depends on the band structure. And for this particular band structure parabola, it looks like, essentially it looks like h bar k over m star, because that's just your k vector, right, from the origin till there, right? Does that make sense? So kx x plus y. So essentially, if the velocity of this is radially going outwards, and the length of that vector, the magnitude of the momentum h bar k, is proportional to how far you from the origin, right? If kx and ky is 0, you're sitting here, that electron is not going anywhere. Its group velocity is 0, right? And then you go here, it's going that way. If you go here, well, it's radially outwards, and it's moving faster, but going that way. I have an electron here that's going very fast, actually the fastest among everything inside, but it's going this way along the y direction, right? Not from the source to drain, but laterally. Does that make sense? So now if I look at this, you have all these electrons, in k space that are going. Some are going in the right direction, some are going at very fast, but going at other angles and all that. And you have a whole distribution of k's now, right? And clearly, this is not the same as a 1D conductor. If you had many of them in 1D, what we'll see later is 1D conductor. If you actually could manage to have a parallel 1D conductors, if you intrinsically do not allow a lateral momentum, okay, you can make better use of the energy in pushing current through. You can make a slightly better. All the energy you supply will go into driving the current. Here, part of the energy will kind of go into electrons that are going in other directions. So that's a kind of a qualitative way of saying what I want to say here. Okay? So that's your group velocity now. Right? All right. So what I wanted to just as a summary, the modes are what connect the classical to the ballistic picture, and depending on dimensionality, the modes are proportional to the physical dimensions. So okay, so now what we are going to do is use this idea and look at the ballistic transistor current and look at what do we mean by, hopefully, transconductance and gain and other things of the ballistic effect. So what I'm going to do, I'm going to essentially solve everything that we need for the ballistic transistor first and then apply it. So once I have this distribution, you can now ask a lot of very interesting questions, and some of these I've asked you to solve. I can ask, what is the current carried by these states, in this situation, the current that is going to the right? You can ask that question. It's a very valid question. It's basically the current that's carried by the right going half circle here. So you can ask that question, and it's a very valid question. And you can imagine that if I have not applied any source drain voltage, that current will be exactly equal to the current going to the left because there's no net current flowing, right? And that is also exactly equal to the current going that way and in any direction you want. That current is still flowing internally. It's just exactly balanced by the other one, right? So, does that make sense? I mean, this is the moment I have filled carriers in the K states, there is already a current flowing inside. It just manages to balance each other out exactly, right? And the whole business of net current will be just to break the symmetry, and then you have net current flow after that. Once you modify it a little bit, then you have you see the net current. Another way to look at it is, so for example, the lateral part of it, if I apply source drain voltage, I won't see the lateral part, but the lateral part of it is clearly visible when you apply a magnetic field. Then you have a Hall effect when you redirect some of the carriers in one direction. And then you go further, you have quantum Hall effect, and we are going to talk about those things later on, quantum Hall and aspects of magnetic field. But how do I calculate the current here? This part I think you should be comfortable because we did it also in the last class. But let me just do it one more time. What is the net current carried by this? I'll outline the procedure as usual. And what I want to say is it's very much dependent on the groove velocity, though. Yeah.
Actually, I have 2 questions from
Sure, please.
the previous part. My first question is that you said if we didn't have those modes which are lateral, it would be better, right?
See, whenever I say better, I mean that if your whole purpose of making this structure is to have the highest amount of current at the smallest amount of voltage, yes.
So, but the number of modes will be reduced, right?
The number of modes will be...
If we don't have those lateral modes.
So you have to quantify it now. You have to quantify it, right? Because you see, you are essentially taking... if I don't have lateral modes, then what we're kind of doing is I've put a lot of 1D conductors in parallel. Then I don't have a circle. I have more like a,
so you mean
squarish
those
thing.
modes just in kx axis. So you mean just...
What I mean is, I have this, and there's like m copies of that.
So you mean all of those m modes, but in just one direction.
Yeah.
But the number of modes will be the same.
Yeah. So exactly. So what I'm trying to say is, instead of this 2D conductor, I have, maybe 100 nanowires or nanotubes in parallel. You will actually manage, as you can see, it depends on how closely you pack and all that stuff, but you can win going that way over a pure 2D conductor.
And the second question is that you said that the number of modes does not depend on the band structure. But I think the number of values will...
Yeah, so the number of modes, the moment I say that I'm going to put this much carriers, right? So the K space is independent, but actually, let me put it this way. So you are absolutely right. You can see the number of values will appear here, right? So the EK won't matter, but the number of values will matter if you want to find the carrier density. That's actually correct. So maybe I should correct myself that the shape of the band structure may not matter, but the number of values will definitely matter because there are GV copies of this, right, in K space. Absolutely, good point. So as a result, if you have, you can draw the conclusions. If you have more values, how will KF change? For the same electron density, your KF will be smaller because you have 6 copies or 4 copies of it. So okay. So now we're going to just calculate the current here, and you can see you can actually go in many directions. If it's been a dream for many people now for the last decade or so. Can I actually couple? So you see, the moment I make a left electrode, a source contact, I am actually coupled to these carriers now because they are filling the right-going states, right? And left electrode, I'm filling these states. And now I'm going to calculate the current of these states. But if you could, by some means, and these are things that nobody knows how to do, but it would be surely very nice to have it because it can do a lot of nice applications. Let's say I take a little, slice here, an arc like that. can I connect to that small window of K's? Does that make sense? I mean, this is an interesting question. Can I have a contact that will only connect to those, right? And not to the all the right-going states? As of now, nobody knows how. So it says what I'm trying to say is, if one could figure out a way to do that, it could lead to some nice applications in the future, right? So generally, I mean, for lack of a better name, they call it smart contacts. Or in each state, here you have upspin and downspin. Can I only connect to the upspins and not the downspins? I mean, these things. I mean, these are not very well known. Right? So people are trying to make these spin filters and things like that. But okay. So what we can so you can see instead of calculate the current for the whole right side, you can calculate the current that's just flowing, in that little thing. Because if I make a contact to that, right, these carriers will be in equilibrium with that electrode, right, with that potential, which could be somewhat different from those, and I can start doing many other things. Okay, so again, going back and invoking our current, expression is Q over dimensions, and then I'm going to pull out my spins and valleys and just sum over the group velocities, right? That's what we have decided to do, right? The current density. And whenever I write that, and we have derived this, right, and used it a couple of times. Whenever I write that, that current is really, as you can see, it's a vector, and the direction of the vector will be determined, and the magnitude will be determined by what portion of the K space you choose to evaluate this. Does that make sense? I mean, if I choose to evaluate over the entire circle, it will be 0, right? Because for every state here, that electron is going that way. There's exactly opposite here that's going that way. They will perfectly balance each other, and the net sum will be 0. Right? When you have not applied a voltage, right? But and on the other hand, if I choose this, you can see the net current will be going that way. Right? If I choose that little slice here. Right? And if I choose that, then the net current is going to the right. You can see that just by symmetry, right? Because there's equal and opposite on both sides. And I will just, do this, So here, again, you have W and L and your spin and valleys. But now, I'm interested in the right-going current, right? So what I'm asking now is I don't want the whole vector. I want the current going in the x direction. From source to drain, or just going in the x direction. And if I ask that question, then instead of retaining the whole group velocity, I only will retain the x component of the group velocity, right? Does it make sense? You just take a projection in the x direction, and that happens to be, this the complete velocity times cosine theta. If you find the angle of any state, if that's the angle. Right. Cosine theta is, k cosine theta is the x-directed velocity. So that's really what you sum over k's. That's h bar by m star, k cosine theta, right? And then f of k, the occupation function. I just want to kind of point this out. Here's a major distinction. Let me actually, is that clear? This is the total k, kx, ky, right? But this is the factor that takes into account, it converts from kx, ky to the kx directed momentum, or x directed value. So you have gs, gv, Planck's constant, pull out all the constants from there, and then there's a m star. And let me already convert it, the sum over all these finely spaced k points into an integral. So I get dkx, dky over 2 pi by L, 2 pi by W. I'm just doing, the standard procedure here. K cosine theta f of k. So that's the whole thing. And so there was, there's a W by L, a W and L here, so they just go, right? They cancel out. The area argument just goes away. And then I have 2 pi squared, which I take outside. And, I think some details of this come out like that. Dkx, dky. And at this point, you should be able to see that, what's the natural symmetry of the problem. It's circular. So I should really move over from Cartesian coordinates to circular coordinates, right? Go from kx, ky to k, k and theta. I should go to those coordinates. And in those coordinates, dkx, ky becomes k d, all right, k dk d theta, right? That's what it becomes, right? And then you kind of choose carefully, if you have asked the question, what is the current going to the right side? The case, you can take it from 0 all the way to infinity, right? Why? Because your Fermi function is going to help you. It's going to kill whatever is above there, high up there, right? So it's just going to decay. But the theta you have to choose carefully. You have to go from, for example, here, you have to go from minus pi by 2 to plus pi by 2, not all around. And you can see right away that if I take theta all around, I'll get a 0 because I'm integrating cosine theta. It's over one whole period, you'll get a 0. But when you integrate cosine theta over a half period, then you get a 2, right? Integral of cosine theta over half period will just give you a 2. Right, and then the rest of k, and that goes from 0 to infinity. And anyway, this looks like I already solved this for you. But so there's k squared dk, and Fermi Dirac function is 1 plus e to the power, the whole. Let me write this part down: ec plus and this is a very important point I'm going to make here, which So what is the kf? I mean, you kind of know. So what is this Fermi level? You already know that based on the carrier density. What is the maximum, right? So that's EF. But the moment I have electrodes, I think you can see it. The right-going carriers are in equilibrium with the left electrode, right? You know that much, right? So they will be in contact with the left electrode. So depending upon whether I have connected them to contacts or not, I should use that here. But in general, what I will write is. You can write it as some Fermi energy here, but that Fermi energy is that of the source, because the source is the left contact, and I'm going to actually just assume I have connected it to the left contact, and then that's the situation. And this part is now in the form of Fermi Dirac integral, and this is the half order, if you know half order Fermi Dirac integral, where the argument so you can see there's some dimensions here, and you can non-dimensionalize it, pull out some factors, but the argument will be the following, and that's the key point here, that it's the Fermi level of the source minus EC over KT, right? So which will be basically, you write E minus this factor, right? So you take it there. That's going to be your argument, and your whole expression here will look like Q GS GV over 2 pi. Let me just write that. I can't remember, but let me just look that up quick, because rather than writing it incorrectly, I should just okay. So it looks like charge. Spin Valley degeneracy is the some 2 pi square factor, Planck's constant by this, and then there's a Fermi Dirac integral f halves. So let me what was that? 2 pi squared h bar by m star. All right, so that's that's how it looks, times the Fermi Dirac integral of half order. Okay. All right, so that's kind of the current going to the right, just the current going to the right, and that's obviously also equal to the magnitude of the current going to the left. It's no different, right? So they're exactly equal when you have no voltage applied on it. Is that clear? I mean, this is what has physically happened is you have somehow managed to fill these modes with electrons, either with a gate or with a modulation doping, meaning the electrons were already there even before you did anything with the gate. And when you have the situation that this is the current that's carried by the right-going states. And now when you connect the electrodes, again, just like for the 1D conductor, you had a right-going Fermi level, which was in equilibrium with the source, and left-going Fermi level in equilibrium with the drain, with the chemical potential of the drain. Similarly, the right-going Fermi level here, which is this term, becomes your mu, or Fermi level of the source or the left contact, and for the left going, it becomes that of the right contact, and the difference is the total current. Okay? So the difference is the total current. And so what's the difference? That's, again, so the total current will be this, the right going minus the left going. And the only difference, you can see the whole thing in the prefactor is constant. It doesn't change. So the total current will be this minus the left going part, right, which is eta sub drain. And let me just make sure that it's clear. What is eta sub source? That is the Fermi level of the source minus conduction band edge over KT. What is eta of drain? It is Fermi level of the drain minus conduction band of the semiconductor over KT. What is eta source minus eta drain? That is Fermi level of source minus Fermi level of drain, right? And that is just Q times the applied voltage, right? So just like we had for the 1D conductor, that's Q times the applied voltage. Let me write the whole thing. Fermi level of the source minus Fermi level of the drain over KT. So that's QV over KT. Right? So that's the equation for the difference of the source and drain Fermi levels. Right? Is that clear? I mean, so it's exactly the same, really not much different from what we had done earlier. Now, so in the last few minutes, what I want to do is tell you a little bit, and I'm not covering this part in detail, but how do you control these source and drain? Because a transistor is not just a source drain device. The very important thing about transistor is there's a third terminal, right? And that plays obviously an extremely important role, which gives and imparts the device the gain and things that you really don't have in a normal two-terminal structure, right? So for example, if I make another ohmic contact to this 2D system, it's a three-terminal device, but it doesn't have something which a transistor has, and that is gain, right? And gain and output decoupling from the input. And let me just explain what that means. Just as a quick picture now, so you have source, drain, and let's again assume I have a 2D conductor or a 2D crystal could be created inside a 3D material. And I've drawn this picture in a way that hopefully will be clearer. You cannot really say that electrons in the source are red and this is green, but just to distinguish them, we say that, well, yeah, I have source electrons and I have drain electrons here. And here's my source injection point. At this point, these electrons in the 2D system, which are sitting in the conduction band K states, have equal and opposite left and right going states. Half of them have come from the source, they're red, right? And half of them have come from the drain, they're green. They're all like waves. I mean, so the moment there's an electron here, it's a wave. It's a wave, so there's no, it's ballistic, right? So there's no decay. So these are in equilibrium with that. And then you go ahead and you actually apply a voltage on the drain. So what does that mean? You kind of pull that down. Right? When you pull that down, there are less green states that are going to the left because now the equilibrium function has gone down, just like we had for 1D conductor. But weirdly, you might think that the red will remain the same because this is really has not changed, right? But the most important thing about the transistor really is that no, it has to change, because the electron density at the source injection point is not controlled by the source or the drain. It's completely not controlled by the source and drain. On the other hand, it's completely controlled by what voltage you put on the gate. If the gate voltage has not changed when you apply the drain voltage here, then the carrier density cannot change. The gate completely capacitively couples and controls what is the electron density at the source injection point. And as a result, what does that mean? All it means is the area of this circle is exactly equal to the area of some of the half circles here. It has to be. If you don't have it, then it's not a transistor. It's gone into a resistive mode, right? Meaning it has no gain. The entire gain, all this stuff comes from this control of gate. If the gate cannot control it, then it's not a transistor. It has no gain. And many times you'll see, results where people claim, oh, this is a great transistor, but you see that the gate has completely lost control. And it's like a so when the gate controls the device, gate has complete control over the source injection point, then the current versus for example, if you apply a drain voltage versus the a drain current, it will look like this. The current will actually saturate very nicely. Then you change the gate voltage, it will saturate at some other point, and we're going to see why. Okay? So it will kind of do that. Right? If the gate loses control over the channel, it will kind of do that. There'll be no saturation. Right? And whenever you see that picture, you know what has happened. The gate has lost control over the channel. It's electrostatically not well designed. And is that clear? So you can see now it's very interesting because as I have fixed the gate voltage and I'm changing the drain voltage, right? So I can start shrinking the green part here, right? Because I'm increasing the drain voltage, right? So it's injecting less and less. So on the other hand, the gate dictates how much charge there is. So the entire area has to remain the same, right? And at some point, you will reach a certain point when all of this left-going green states will disappear, right? I mean, it's become the drain voltage is very high. It cannot inject anymore at all, right? I mean, there's some, but it's not much anymore, right? This will become shrunk. And now everything is going to the right, right? And once you reach this situation, you can see that now I can apply more drain voltage, but nothing's going to change anymore, right? The shape will remain like this because the drain is not doing anything anymore, right? Is that clear? I mean, once you reach the situation, it's one half circle to the right, and you apply even more drain voltage, it remains like that, right? And because we know what is the current, we just calculated the current for the right-going states. The right-going state current is just that, right? You are summing all the group velocities in that half circle, right? The x directed. So the current is sum of all these k cosine thetas here. That is not changing anymore, right? Once you reach the situation, therefore the current saturates. There's no more change in current with the drain voltage. Does that make sense? I mean, because so the drain current increases and then it just saturates because all of them are now moving to the right. There's nothing more to do, right? So that's the maximum current you can get. And when the gate says that, well, I want less electrons there, then it will saturate at a lower level and a lower level and so on. So that's the modulation of the gate. Similarly, when the gate starts saying that I go to very low carrier densities, all the carriers are going to the right, but then you go through a log scale behavior, meaning the carrier density goes down exponentially, and then you're kind of shrinking the right-going state into the area is now shrinking, when you change the gate voltage and we want to remove the electrons. All these are the same electron density, meaning these curves are explaining why it's 0 initially because they're same, why it goes here, because all of them are moving to the right now. Right? Similarly, you can now change the gate voltage and say that, well, if I start here, I was increasing the drain voltage, and then I start reducing my gate voltage, then you kind of shrink the whole circle down to 0. The current becomes very, very low now, right? So that's on to off, and that's your amplifier situation where you have output, the gain. Okay? And what is the gain? See, I'm a little bit out of time today, but what is the gain of the transistor? The way to look at it is, if I the first thing is you can see right away that it is like the source to drain contact is like a resistor, at least in this part of the picture. It's like a resistor I is proportional to V. Source to drain, but that resistance value is variable. Right? It's not the same. It's just not the same at all voltage. It's variable. And what controls this is neither the source nor the drain. What is the resistance controlled by? It's controlled by the gate, right? The third terminal, right? So, the origin of that was really, I think we've mentioned this a couple of times, is so the resistance of this channel, the job of controlling the resistance has been transferred to the third terminal, which, by the way, does not allow any electron movement between them. It's remotely controlling it with field effect. So that's the transferred resistor or the transistor, right? The name originates from there. But more importantly, the gain of it, for example, if you want to look at it, is and this we can, I think I'm a little bit out of time today, but what we can do is in the next class, I'll try to finish up this argument. The gain of the transistor comes from the following, that if I, at a certain gate voltage, I am flowing a certain drain current, right? And let's say it's grounded and I have a VDS here, right? So some current is flowing. And I say that I'm going to change the gate voltage by a little bit, right? I'm going to change the gate voltage by some amount. What do I mean by that? What I mean by that is, physically, what am I doing when I change the gate voltage? It's connected to a battery. So I kind of pull out electrons. Basically, I put some electrons on the gate metal. Right? So for example, that's a negative voltage. So put some extra electrons on the gate metal. Let's say I put 10 electrons on the gate metal. So, I mean, I'm just doing some rough numbers, 10 electrons. Right? So that will effectively couple into the channel of the 2-DAG, and it will change it will increase the current, for example, by maybe 10 to the power 4 or something like that. Does that make sense? I mean, for example, if you are sitting here at this point in gate voltage, a log scale in on to off. I'm sitting here, and I increase my voltage by this much, right? And my current goes up by 10 to the power 4, on to off to on, or something like that. I mean, this is just a rough way of looking at it. So by changing something by a small amount here, you're getting a large change out here, right? So that's the idea of gain. That's a DC gain, which is really not terribly that important as much as if I have an AC signal, I have a very small AC riding signal, and the output here is really, goes up by a large amount. This factor in transistors is called transconductance, and we will discuss this in the next class. I'll just stop here, okay? It goes as a derivative of drain current versus the gate voltage. So that's the transconductance, which has units of 1 over ohm or Siemens. So we'll look at that. Larger is the transconductance, more is the gain, and So that's always a quest. You want more gain, more on-off ratios, smaller voltages for switching, and so on. So there are some things I didn't discuss. One of them was how does the carrier density depend on gate voltage? And that's typically something I sent out an email for you to look up where to look up how do you calculate that electrostatic problem. But it's summarized also in the slides here. Please read that up. The carrier density dependence on gate voltage is the key behind the transistor. The transport gives you the details, of the numbers, but the control is really with the electrostatic control. Okay? And here's a slide that summarizes everything about the ballistic transistor. There are a lot of equations and all, but once you realize what they are, this is the procedure. And if you want to calculate the current, just go through this procedure, right? And then you get the current. And you are going to do that for your assignment problem. So, okay, good. So I'm done. No class this Friday. And we meet next Monday in the class.
Excuse me. Yeah. Do you have a few moments? Sure. My question is about...
I should just give